science for sleep. Right now, as you settle in, as you find that comfortable position, as the world outside grows quiet and still, I want you to consider something extraordinary. Something so fundamental, so woven into the fabric of everything you have ever seen, everything you have ever touched, everything you have ever known, that you probably never stopped to question it. Light. That gentle glow from your screen, the soft illumination in your room, the distant twinkle of stars that you might see if you glanced out your window right now. Light is everywhere. It is the most familiar thing in the universe. And yet, light holds a secret so profound, so deeply strange, that when physicists first uncovered it, it shattered everything humanity thought it knew about space, about time, about the very nature of reality itself. That secret is this: light has a speed limit. It travels at exactly 299,792,458 meters per second. Not approximately, not roughly. Exactly that number. And nothing in the universe, nothing that carries information, nothing that carries energy, nothing that has ever existed or will ever exist, can travel faster. But why? Why does light have a speed limit at all? Who set that limit? What would happen if that limit were different, even by a tiny amount? And here is the question that will keep your mind gently spinning as you drift tonight. Is the speed of light actually about light at all, or is it something far, far deeper? Tonight, we are going on a journey, a long, deep, meditative journey through one of the greatest mysteries in all of science. We are going to trace this question from the ancient world, through the Renaissance, through the golden age of physics, through Einstein's revolutionary insights, through the bizarre quantum world, all the way to the cutting edge of modern theoretical physics. By the time we are done, you will never look at a beam of sunlight, a distant star, or even the glow of a candle the same way again. So settle in, get comfortable, let your breathing slow, and let us begin. Let me start by telling you something that might surprise you. Light is fast, incredibly, almost incomprehensibly fast. If you could somehow shine a flashlight and watch the beam travel, you would see it race away from you at nearly 300,000 kilometers every single second. That is fast enough to circle the entire Earth 7.5 times in the span of a single heartbeat. If you could travel at the speed of light, you could reach the moon in just over 1 second. You could reach the sun in about 8 minutes. You could leave our solar system and arrive at the nearest star, Proxima Centauri, in a little over 4 years. Light is so fast that for most of human history, people simply assumed it was instantaneous. They thought that when you opened your eyes, you saw things as they were, right now, in this very instant. But here is where it starts to get interesting. Light, as fast as it is also incredibly slow. And I mean that seriously. Our Milky Way galaxy is about 100,000 light-years across. That means a beam of light, traveling at its extraordinary speed, would take 100,000 years just to cross from one side of our galaxy to the other. And our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. The observable universe itself is about 93 billion light-years across. These distances are so vast, so staggeringly enormous, that even at the speed of light, the universe is effectively infinite from a practical standpoint. You could travel at the speed of light for your entire lifetime, and not even scratch the surface of what is out there. And that leads to one of the most beautiful and haunting facts in all of science. When you look up at the night sky and see a star, you are not seeing that star as it is right now. You are seeing it as it was years ago, maybe hundreds of years ago, maybe thousands of years ago, because the light from that star took that long to reach your eyes. Some of the stars you see in the night sky might not even exist anymore. They might have exploded, collapsed, died, and vanished long before you were born. But their light is still traveling, still journeying across the void, carrying an ancient message from a star that no longer exists. You, lying in your bed right now, are looking backward through time every time you glance at the sky. Telescopes are time machines. The deeper we look into space, the further back in time we see. The James Webb Space Telescope has captured light from galaxies that formed just a few 100 million years after the Big Bang, over 13 billion years ago. That light has been traveling for almost the entire history of the universe, crossing unimaginable distances, dodging galaxies and dust clouds and the expanding fabric of space itself, just to land on a mirror that humans built and pointed at the sky. And all of this, every bit of it, is governed by that one number. 299,792,458 meters per second. The speed of light. The universal speed limit, the cosmic speed limit. The number that defines what is possible and what is forever out of reach. Now, before we dive deeper, I want to share some facts with you. Facts that I think will help you appreciate just how strange and wonderful this topic really is. Here's the first one. If the sun were to suddenly vanish, just disappear entirely, we would not know about it for 8 minutes and 20 seconds. For those 8 minutes, we would still see the sun in the sky. We would still feel its warmth. We would still orbit where it used to be. Because the information about its disappearance, traveling at the speed of light, would take that long to reach us. For 8 minutes, we would be living in a universe that no longer matches reality. Here's another one. Nothing with mass has ever, in the entire history of the universe, traveled at the speed of light. Not a single atom, not a single electron, not a single grain of sand. Every particle with mass that has ever existed has always traveled slower than light, and not just a little slower. Even in our most powerful particle accelerators, where we accelerate protons to 99.9999991% of the speed of light, they never quite reach it. They get closer and closer, but there's always that tiny, unbridgeable gap. It is as though the universe has drawn a line and said, "This far, no further." Here is one more, and this one is perhaps the most mind-bending of all. From the perspective of a photon, a particle of light, time does not exist. A photon does not experience time. From the moment it is created, whether in the heart of a star or in the filament of a light bulb, to the moment it is absorbed, whether by your eye or by a detector on a telescope, no time passes for the photon at all. From a photon's perspective, it is everywhere along its path simultaneously. It is created and destroyed in the same instant. A photon that traveled from a galaxy 13 billion light-years away experienced that entire journey as a single, timeless moment. 0 seconds. No duration at all. What kind of universe allows that? What kind of reality makes that possible? That is what we are going to explore tonight. Now, if you are the kind of person who loves deep dives into the mysteries of the universe, if you love falling asleep to the sound of someone unraveling the secrets of reality, then you are in the right place. I would love for you to be part of this journey not just tonight, but for many nights to come. So, if you have not already, take a moment to subscribe to this channel. Hit that bell icon so you never miss a new exploration. And drop a comment down below telling me this. If you could travel at the speed of light, where in the universe would you go? I genuinely read every comment, and I love hearing what captures your imagination. Also, a simple like on this video makes a bigger difference than you might think. It helps other curious minds find this content, and it lets me know that you want more deep, meditative science journeys like this one. All right, Now let us dive into the heart of the mystery. Let us start at the very beginning, with the simplest and most profound question. What is light? It seems like such a basic question. We all know what light is, right? It is that thing that comes from the sun, from light bulbs, from candles, from screens. It is what allows us to see. It is warm. It is bright. It fills our days and fades with the night. But the truth is, for most of human history, nobody had any idea what light actually was. And the story of how we figured it out is one of the most beautiful stories in all of science. Let us travel back in time, thousands of years, to ancient Greece. The Greek philosophers were among the first to seriously ponder the nature of light, and their ideas were fascinating, creative, and mostly wrong. The philosopher Empedocles, who lived around 490 to 430 BCE, was one of the first to propose that light actually travels from one place to another, that it is not simply present everywhere instantaneously. He suggested that light comes from the goddess Aphrodite and travels to us through space. Beautiful, poetic, but not quite right. Then there was Plato, one of the most influential thinkers in Western history. Plato proposed something called the emission theory of vision. He believed that your eyes actually shoot out invisible beams, like tiny flashlights, and when those beams touch an object, you see it. So, in Plato's model, you do not see because light enters your eyes. You see because your eyes reach out and touch the world. It is a charming idea, and it has a certain intuitive appeal. After all, it does feel like you are actively looking at things, reaching out with your gaze. But of course, if this were true, you would be able to see in the dark, because your eye beams would illuminate everything they touched. Aristotle had a different idea. He thought light was not a thing that traveled, but a state, a condition of the medium between you and the object. He compared it to how water can be still or agitated. Light, for Aristotle, was the medium being in a particular state. This is closer to the truth in some ways, but still far from the full picture. The real breakthrough in understanding light came from the Islamic Golden Age, and specifically from one of the greatest scientists who ever lived, a man whose name should be as famous as Newton or Einstein, but sadly often goes unrecognized in the Western world. His name was Ibn al-Haytham, also known in the Latin West as Al-Hazan. He was born in Basra, in what is now Iraq, around the year 965 CE, and his contributions to science were absolutely revolutionary. Ibn al-Haytham wrote a monumental work called the Book of Optics, published around the year 1011. In it, he systematically demolished the emission theory of vision. He argued, using careful reasoning and experimentation, that light comes from external sources like the sun or a candle, bounces off objects, and then enters your eyes. You do not see because your eyes emit beams. You see because light from the world enters your eyes. This might seem obvious to us now, but in the year 1011, this was a radical idea. Ibn al-Haytham proved it through a variety of ingenious experiments. He studied the camera obscura, a dark room with a small hole in one wall. Light from outside enters through the hole and projects an inverted image on the opposite wall. He analyzed the geometry of this phenomenon in detail and showed how it was consistent with his model of light entering the eye from external sources. He studied reflection and refraction. He explored how light bends when it passes from one medium to another, like from air into water. He even studied the anatomy of the human eye and made important observations about how it functions as an optical instrument. In many ways, Ibn al-Haytham invented the scientific method itself. He insisted on empirical evidence, on testing hypotheses through experiments, on rejecting ideas that did not match observations, no matter how ancient or respected those ideas were. He was a scientist in the truest sense of the word, over 600 years before Galileo, and his work on optics remained the most authoritative text on the subject for centuries. If there is one name you remember from tonight's journey, let it be his. Now, let us leap forward several hundred years to the Europe of the 17th century, where a fierce debate was raging about the fundamental nature of light. On one side stood Sir Isaac Newton, arguably the most influential scientist in history. Newton believed that light was made of tiny particles, which he called corpuscles. These corpuscles were shot out by luminous objects like candles in the sun, traveled in straight lines, bounced off mirrors, and entered your eyes. Newton demonstrated his theory with one of the most famous experiments in all of science, the prism experiment. He took a beam of white sunlight and passed it through a glass prism, and the white light split into a beautiful rainbow of colors: red, orange, yellow, green, blue, indigo, and violet. Newton concluded that white light was actually a mixture of all these colors, and the prism separated them because different corpuscles traveled at slightly different speeds through the glass. This was a brilliant insight, and it was largely correct, though for different reasons than Newton supposed. Newton's particle theory of light explained many observations beautifully. It explained why light travels in straight lines, creating sharp shadows. It explained reflection, the bouncing of light off mirrors. It even explained refraction, the bending of light when it enters water or glass, though Newton's explanation of refraction required that light travel faster in denser media, which, as we will see, turned out to be wrong. On the other side of the debate stood Christian Huygens, a Dutch physicist and mathematician of enormous talent. Huygens proposed, in 1678, that light was not a particle at all, but a wave. Just as sound is a wave that travels through air, Huygens believed light was a wave that traveled through some medium. This wave theory explained phenomena that Newton's particle theory struggled with, particularly diffraction, which is the way light bends around obstacles and spreads out after passing through narrow openings. But Huygens' theory had what seemed like a fatal problem. If light is a wave, what is it a wave of? Sound needs air. Water waves need water. What was light waving in? Huygens proposed that all of space was filled with an invisible, intangible substance called the luminiferous ether. Light was a wave in this ether, just as sound is a wave in air. The ether was everywhere, permeated everything, was perfectly transparent, and yet somehow rigid enough to transmit waves at an enormous speed. It was an elegant idea, but it raised as many questions as it answered. For now, though, the debate between Newton's particles and Huygens's waves raged on, with Newton's enormous reputation tipping the scales in favor of particles for over a century. The tide began to turn in 1801, when a young English polymath named Thomas Young performed one of the most important experiments in the history of physics. It is called the double-slit experiment, and to this day it remains one of the most profound and mysterious experiments ever conducted. Here is what Young did. He took a beam of light and shone it at a barrier that had two thin, parallel slits cut in it. Behind the barrier, he placed a screen. Now, if light were made of tiny particles, as Newton proposed, you would expect to see two bright strips on the screen, one behind each slit. The particles would pass through one slit or the other and pile up in two bands. But that is not what Young saw. Instead, he saw a pattern of alternating bright and dark bands spread across the screen. This is called an interference pattern, and it is the unmistakable signature of waves. Here is how it works. When a wave passes through two slits, each slit becomes a new source of waves. These waves spread out and overlap. Where two wave crests meet, they reinforce each other, creating a bright band. Where a crest meets a trough, they cancel each other out, creating a dark band. This is exactly what you see when you drop two pebbles into a still pond and watch the ripples interact. Young's experiment conclusively demonstrated that light behaves as a wave. This was devastating to Newton's corpuscular theory. The interference pattern simply could not be explained by particles flying through slits. It required waves spreading and overlapping and interfering with each other. The wave theory of light was vindicated, and a new era of optics began. Over the next few decades, other scientists, particularly the French physicist Augustin Jean Fresnel, built a rigorous mathematical framework for wave optics. Fresnel showed that light is specifically a transverse wave, meaning it oscillates perpendicular to its direction of travel, and he explained the phenomenon of polarization, where light vibrates in a particular direction. Everything pointed to light being a wave. But the question remained, a wave of what? What was this luminiferous ether that supposedly filled all of space? The answer came from an unexpected direction, and it came from one of the most brilliant minds in the history of science. His name was James Clerk Maxwell, a Scottish physicist who, in the 1860s, achieved something truly extraordinary. Maxwell was studying the relationship between electricity and magnetism. Earlier scientists, particularly Michael Faraday, had shown that electricity and magnetism were deeply connected. A changing magnetic field creates an electric field. A changing electric field creates a magnetic field. Maxwell took these observations and wove them into a unified mathematical framework, a set of 4 elegant equations that described all of electromagnetism. These are now known as Maxwell's equations, and they are among the most important equations in all of physics. But here is where the magic happened. When Maxwell solved his equations for a region of empty space with no charges or currents present, he found something astonishing. His equations predicted the existence of self-sustaining waves, waves in which an oscillating electric field creates an oscillating magnetic field, which in turn creates an oscillating electric field, and so on, leapfrogging through space. These electromagnetic waves required no medium. They could travel through the vacuum of empty space, propelled by nothing more than the interplay between electric and magnetic fields. And when Maxwell calculated the speed at which these electromagnetic waves would travel, he got a number. A very specific number. He calculated their speed to be approximately 310,000 kilometers per second. Maxwell immediately recognized this number. It was, within the margin of experimental error, exactly the measured speed of light. This was one of those moments in the history of science that changes everything. Maxwell had not set out to explain light. He had set out to understand electricity and magnetism. But his equations were telling him something profound. Light is an electromagnetic wave. Light is not some mysterious entity separate from electricity and magnetism. Light is electricity and magnetism, dancing together in perfect synchrony, racing through space as a self-sustaining wave. This was one of the greatest unifications in the history of physics. Before Maxwell, there were 3 seemingly separate phenomena: electricity, magnetism, and light. After Maxwell, they were all one thing. One force, one set of equations, one beautiful, unified description, and Maxwell's equations made another prediction. They said that electromagnetic waves could have any wavelength, not just the wavelengths we can see. Visible light, the rainbow of colors from red to violet, is just a tiny sliver of a vast electromagnetic spectrum. Below visible light, at longer wavelengths, are infrared radiation, microwaves, and radio waves. Above visible light, at shorter wavelengths, are ultraviolet radiation, X-rays, and gamma rays. All of these are the same thing: electromagnetic waves. All of them travel at the same speed, the speed of light. The radio waves carrying your favorite music travel at the same speed as the gamma rays from a distant supernova. The microwaves heating your food travel at the same speed as the X-rays at the dentist. It is all light in the broadest sense, and it all moves at 299,792,458 meters per second. But the story of light was far from over. Just when physicists thought they had it figured out, just when Maxwell's beautiful wave theory seemed to explain everything, the universe threw another curveball. Actually, it threw several. And they came from a direction nobody expected: the quantum. It started in the year 1900 with a German physicist named Max Planck. Planck was studying something called blackbody radiation, which is the light emitted by hot objects. Classical physics predicted that hot objects should emit infinite amounts of ultraviolet light, a prediction that was clearly wrong and was known as the ultraviolet catastrophe. To fix this problem, Planck made a desperate assumption. He assumed that energy is not continuous, not infinitely divisible, but comes in discrete packets. He called these packets quanta, from the Latin word for how much. Planck's assumption worked. It perfectly predicted the spectrum of blackbody radiation. But Planck himself considered it a mathematical trick, not a reflection of reality. He did not believe energy actually came in packets. He thought the continuous nature of energy would eventually be restored. He was wrong. In 1905, a 26-year-old patent clerk in Bern, Switzerland, took Planck's idea and ran with it. His name was Albert Einstein. In one of his 4 miraculous papers published that year, Einstein tackled a phenomenon called the photoelectric effect. When you shine light on certain metals, electrons are ejected from the metal's surface. Classical wave theory predicted that brighter light should eject faster electrons, but experiments showed that brightness only affected the number of electrons ejected, not their speed. The speed of the ejected electrons depended on the frequency, the color of the light. Einstein explained this by proposing that light itself is quantized. It comes in discrete packets, which we now call photons. Each photon carries a specific amount of energy proportional to its frequency. E equals h times f, where h is Planck's constant and f is the frequency. A photon of blue light carries more energy than a photon of red light. When a photon hits a metal surface, it transfers all its energy to a single electron. If that energy is enough to overcome the binding forces holding the electron in the metal, the electron flies out. Higher frequency means more energetic photons, which means faster electrons. Lower frequency means less energetic photons, and if the frequency is too low, the photons simply do not have enough energy to knock electrons loose, no matter how bright the light is. Einstein's explanation was beautifully simple and perfectly matched the experimental data, but it had a deeply unsettling implication. Light is a particle, a photon, a little packet of energy. But wait. Thomas Young's double-slit experiment had already proved, beyond any doubt, that light is a wave. Waves interfere, waves diffract, waves create those alternating bright and dark bands. Particles do not do that. So which is it? Is light a wave or a particle? The answer, as 20th century physics would gradually reveal, is that light is both, and neither. Light exhibits wave-like behavior in some experiments and particle-like behavior in others. It is not that light is sometimes a wave and sometimes a particle, switching between the two. It is that light is something fundamentally new, something that does not have an analogy in our everyday experience. It is a quantum object, and quantum objects simply do not behave like anything we encounter in our normal lives. This is called wave-particle duality, and it is one of the central mysteries of quantum mechanics. A single photon, fired at the double slits, will create an interference pattern over time, as if it went through both slits simultaneously and interfered with itself. A single photon, going through two slits at once, interfering with itself. Reality, at its most fundamental level, is far stranger than anything we could have imagined. And at the heart of this strangeness, at the heart of waves and particles and quanta and fields, there is that one constant: the speed of light. Every photon, regardless of its energy, regardless of its frequency, regardless of whether it is a radio wave or a gamma ray, travels at exactly the same speed in a vacuum. Always, without exception. Let that sink in for a moment as you lie there. Every single photon in the universe moves at the same speed. The faint red glow from a distant dying star and the blinding gamma ray from a supernova explosion travel at exactly the same speed. Why? What connects them? The answer is that the speed of light is not really about light at all. It is about something much, much deeper. But to understand that, we need to go on a journey through history. The history of humans trying to measure the speed of light. For most of recorded history, humans believed that light traveled instantaneously. If you lit a candle in a dark room, the light was just there, everywhere in the room, the moment the flame caught. There was no sense of delay, no sense of the light spreading outward like ripples in a pond. The great Aristotle himself believed that light was instantaneous. And given how fast light actually is, this was a perfectly reasonable assumption. After all, light circles the Earth 7.5 times in 1 second. No human could perceive such a thing. But not everyone agreed that light was instantaneous. Some thinkers, going back to the ancient Greeks and the Islamic scholars, suspected that light took time to travel, even if that time was incredibly short. And in the 17th century, one of the greatest scientists of the era decided to test this question directly. His name was Galileo Galilei. Around 1638, Galileo devised a simple but clever experiment. He and an assistant each carried a covered lantern. They stood on two hilltops separated by about a mile. Galileo uncovered his lantern. When the assistant saw the flash, he uncovered his lantern in response. Galileo would measure the time between uncovering his lantern and seeing the return flash. If light took time to travel, there should be a measurable delay. But there was no measurable delay. The response seemed instantaneous, no matter how far apart they stood. Galileo correctly concluded that either light was instantaneous, or it was so incredibly fast that the delay was too short for humans to detect. He was right about the second possibility. The problem was that light travels so fast that it would traverse the distance between those hilltops in about 10 millionths of a second, far, far less than human reaction time. The experiment was clever but doomed. Measuring the speed of light would require either much larger distances or much more precise instruments. The first successful measurement of the speed of light came in 1676, and it came not from an experiment on Earth, but from careful observations of the heavens. A Danish astronomer named Ole Rømer was studying the moons of Jupiter, specifically the innermost large moon, Io. Io orbits Jupiter roughly once every 42 hours, and it regularly passes behind Jupiter, disappearing from view in a predictable eclipse. Rømer was timing these eclipses as part of a project to create a reliable astronomical clock. And he noticed something strange. The eclipses were not perfectly regular. Sometimes they happened earlier than predicted, and sometimes later. The discrepancy followed a pattern. When Earth was moving toward Jupiter in its orbit, the eclipses happened slightly early. When Earth was moving away from Jupiter, they happened slightly late. Rømer had a brilliant insight. The irregularity was not in Io's orbit. Io was perfectly regular. The irregularity was in the time it took light to travel from Jupiter to Earth. When Earth was closer to Jupiter, the light had a shorter distance to travel, and the eclipses appeared to happen a little early. When Earth was farther from Jupiter, the light had a longer distance to travel, and the eclipses appeared to happen a little late. By measuring the total discrepancy over the course of a year, Romer calculated how long it took light to cross the diameter of Earth's orbit. His result was that light took about 22 minutes to cross Earth's orbit, which gave a speed of about 220,000 kilometers per second. By modern standards, this was about 26% too low, but it was a monumental achievement. For the first time in human history, someone had demonstrated that light has a finite speed. It does not travel instantaneously. It takes time, and Romer had measured that time. The scientific community was stunned. Many resisted the idea, clinging to the ancient belief in instantaneous light. But the evidence was clear, and over the following decades, Romer's result was gradually accepted. Light was fast, astonishingly fast, but it was not infinite. It had a speed, and that meant that light was something, some kind of entity or disturbance, traveling through space, moving from one place to another, taking time to do so. It was a thing, and things can be studied. The next major confirmation came in 1729, from an English astronomer named James Bradley. Bradley was trying to measure stellar parallax, the tiny apparent shift in the position of nearby stars caused by Earth's motion around the Sun. He did not find parallax, but he found something else entirely: stellar aberration. Bradley noticed that stars appeared to shift their positions in a tiny elliptical pattern over the course of a year, and this pattern was in a different direction than what parallax would produce. After much thought, Bradley realized the shift was caused by the combination of the speed of light and the speed of Earth's motion. It is similar to how rain, falling straight down on a still day, appears to fall at an angle when you are running. Because Earth is moving through space, the light from a star appears to come from a slightly different direction than it would if Earth were stationary. The amount of this aberration depends on the ratio of Earth's speed to the speed of light. By measuring the aberration, Bradley calculated the speed of light to be about 301,000 kilometers per second, an impressively accurate result that confirmed Romer's discovery independently and with greater precision. But astronomers wanted to measure the speed of light on Earth, not just from astronomical observations. The first person to achieve this was a French physicist named Hippolyte Fizeau in 1849. Fizeau's experiment was ingenious. He set up a rapidly spinning toothed wheel and a mirror about 8 kilometers away. He shone a beam of light through a gap between two teeth of the wheel. The light traveled to the distant mirror, reflected back, and returned to the wheel. If the wheel was spinning at just the right speed, the returning light would pass through the next gap and be visible. If the wheel was spinning too fast or too slow, the returning light would be blocked by a tooth. By adjusting the speed of the wheel until the returning light was visible, Fizeau could calculate the time it took light to make the round trip. His result was about 313,000 kilometers per second. Not perfect, but remarkable for a tabletop experiment. The technique was refined just a few years later by Léon Foucault, who replaced the toothed wheel with a rotating mirror, allowing for greater precision. In 1862, Foucault measured the speed of light at approximately 298,000 kilometers per second, much closer to the modern value. Foucault's experiment had another crucial result. He showed that light travels slower in water than in air. This was a critical finding because Newton's particle theory predicted that light should travel faster in denser media, while the wave theory predicted the opposite. Foucault's measurement confirmed the wave theory's prediction and dealt another blow to the corpuscular model. The most dedicated measurer of the speed of light in history was the American physicist Albert Abraham Michelson. Michelson was obsessed with precision. He spent decades, from 1879 to the 1920s, refining and improving methods to measure C with ever greater accuracy. His measurements became legendary for their precision, and in 1907 he became the first American to win the Nobel Prize in Physics, specifically for his optical precision instruments and the investigations carried out with them. Michelson's final measurements in the 1920s gave a value of 299,796 kilometers per second, astonishingly close to the modern defined value of 299,792.458 kilometers per second. But Michelson's most important contribution was not his measurement of the speed of light. It was an experiment that tried to detect the medium through which light traveled, the luminiferous ether. And the result of that experiment would lead directly to the most profound revolution in the history of physics. In 1983, the scientific community made a remarkable decision. They stopped trying to measure the speed of light more precisely. Instead, they redefined the meter itself in terms of the speed of light. The speed of light was fixed, by definition, at exactly 299,792,458 meters per second. The meter was then defined as the distance light travels in vacuum in one 299,792,458th of a second. This might seem like a subtle change, but it is actually deeply profound. We no longer measure the speed of light. We define our system of measurement around it. The speed of light is the ruler against which we measure everything else. It is not just a number. It is a fundamental constant of nature that we have woven into the very fabric of how we measure reality. Think about that for a moment. The speed of light is so fundamental, so reliable, so absolutely constant, that we base our entire system of measurement on it. It is the one thing in the universe that never changes, that every observer, in every situation, in every corner of the cosmos will always agree on. And that constancy, that absolute invariance, is the key to everything we are about to explore. Now, let us go back to the 19th century, to the greatest failed experiment in the history of science. If light is a wave, as Maxwell had proved, then it should travel through some kind of medium. Sound waves need air, water waves need water. Waves on a guitar string need the string. By analogy, light waves should need something to wave in. That something was the luminiferous ether. The ether was imagined as a substance that filled all of space, permeated all matter, and served as the medium through which light propagated. It had to have some extraordinary properties. It had to be incredibly rigid, because it had to transmit waves at the enormous speed of light. You see, stiffer media transmit waves faster, and the speed of light is so great that the ether would have to be far more rigid than steel. Yet, it also had to be perfectly transparent, because we can see through it. And it had to offer no resistance to the motion of planets and other celestial bodies, because the Earth and other planets move through space without any apparent drag. It was a strange substance, to say the least. But physicists accepted its existence because they could not imagine waves without a medium. The ether was as much a part of 19th century physics as gravity. Its existence was simply assumed, but assumption is not evidence. And in 1887, two American physicists set out to detect the ether directly. Their names were Albert Michelson and Edward Morley, and their experiment is now one of the most famous in all of physics. The idea was simple and elegant. If the ether fills all of space and is stationary, then Earth, as it orbits the Sun at about 30 kilometers per second, should be moving through the ether. This means that from Earth's perspective, there should be an ether wind blowing past us. Light traveling in the direction of this wind should be carried along slightly, like a boat going downstream, and would appear to move faster. Light traveling against the wind should be slowed, like a boat going upstream, and light traveling perpendicular to the wind should be somewhere in between. Michelson and Morley built an extraordinarily sensitive instrument called an interferometer. It split a beam of light into two beams traveling in perpendicular directions, then reflected them back and recombined them. If the two beams traveled at different speeds because of the ether wind, the recombined light would show a characteristic interference pattern. By rotating the entire apparatus, they could look for changes in this pattern as the beams aligned with and against the ether wind. The experiment was conducted with meticulous care. Michelson, remember, was the world's leading expert on optical precision. The interferometer was mounted on a massive stone slab floating in mercury to isolate it from vibrations. The expected effect was small, but well within the instrument's ability to detect. They looked, they measured, they rotated the apparatus. They repeated the experiment at different times of day, at different seasons of the year, and they found absolutely nothing. No difference, no ether wind, no shift in the interference pattern. The speed of light was the same in every direction, regardless of Earth's motion. This was baffling. It was as if you were running through the rain, and the rain was hitting you at exactly the same speed from every direction, no matter which way you turned or how fast you ran. It made no sense within the framework of classical physics. The ether, if it existed, should produce a detectable wind, but there was none. The Michelson-Morley experiment is often called the most famous failed experiment in history. It failed to detect the ether, but that failure was one of the most productive failures in all of science because it forced physicists to confront a deeply uncomfortable truth. Either the ether did not exist, or something was very wrong with their understanding of space and time. The physics community scrambled to explain the null result. Several clever hypotheses were proposed. One idea, called the ether drag hypothesis, suggested that the Earth dragged the ether along with it, like a moving ship drags water in its vicinity. If the ether near Earth were moving with Earth, there would be no ether wind to detect. But this idea was quickly shown to conflict with other observations, particularly the aberration of starlight that James Bradley had discovered. A more promising explanation came from the Irish physicist George Fitzgerald and the Dutch physicist Hendrik Lorentz, working independently. They proposed that objects physically contract, shrink, in the direction of their motion through the ether. This contraction, now called the Lorentz-Fitzgerald contraction, would be exactly the right amount to cancel out the expected time difference in the Michelson-Morley experiment. Lorentz went further, developing a set of mathematical transformations that described how lengths and times should change for objects moving through the ether. These Lorentz transformations perfectly accounted for the null result of the Michelson-Morley experiment, but they were ad hoc. They were patches, fixes designed specifically to save the ether theory. There was no deeper explanation for why objects should contract or why time should change. It was as if nature were conspiring, through some cosmic coincidence, to make the ether undetectable. The great French mathematician and physicist Henri Poincaré came tantalizingly close to a full understanding. He recognized the mathematical significance of the Lorentz transformations and discussed the principle of relativity, the idea that the laws of physics should be the same for all observers in uniform motion. But Poincaré never took the final leap. He never abandoned the ether. He never recognized the full revolutionary implications of what the mathematics was telling him. That leap was left to someone else, someone who was not burdened by decades of ether thinking, someone young, audacious, and willing to throw out assumptions that everyone else took for granted. The year was 1905. The place was Bern, Switzerland, and the person was Albert Einstein, a 26-year-old clerk in the Swiss patent office. Einstein was not a professor. He was not at a major university. He had struggled to find an academic position after completing his degree. He worked 6 days a week examining patent applications. But in his spare time, in the evenings and on his day off, he was thinking about the deepest questions in physics. And in 1905, his thinking culminated in what is now known as his Annus Mirabilis, his miracle year, one of the most extraordinary bursts of creativity in the history of human thought. In that single year, Einstein published 4 papers, any one of which would have been enough to secure his place in the pantheon of great scientists. The first paper explained the photoelectric effect, establishing that light comes in quanta, and earning him the Nobel Prize. The second paper explained Brownian motion, providing definitive evidence for the existence of atoms. The third paper introduced the special theory of relativity, and the fourth paper derived the most famous equation in all of physics, E equals mc squared. But it is the third paper that concerns us tonight. It was titled, On the Electrodynamics of Moving Bodies, and it would utterly transform our understanding of space, time, and the speed of light. Einstein's paper began not with complex mathematics, but with a simple thought experiment that had been bothering him since he was 16 years old. He asked himself, what would it look like if I could ride alongside a beam of light? If you could travel at the speed of light, keeping pace with a light wave, what would you see? According to classical physics, you should see a frozen electromagnetic wave, an electric and magnetic field oscillating in space but not moving, like a snapshot of a wave on the ocean. But here was the problem. Maxwell's equations do not allow for stationary electromagnetic waves. An electromagnetic wave, by its very nature, must be moving. If it stops, it ceases to exist. The equations do not have solutions for frozen light. This bothered Einstein enormously. If you could travel at the speed of light, you would see something that Maxwell's equations say cannot exist. Something was wrong. Either Maxwell's equations were wrong, which seemed unlikely given their spectacular success, or our understanding of motion was wrong. Einstein chose to trust Maxwell's equations and throw out the old understanding of motion. Einstein built his theory on 2 deceptively simple postulates. The first was the principle of relativity. The laws of physics are the same in all inertial reference frames. An inertial reference frame is simply one that is moving at a constant velocity, not accelerating. This principle was not new. Galileo had stated something similar centuries earlier. If you are on a smooth sailing ship below deck with no windows, you cannot tell whether the ship is stationary or moving at a constant speed. No experiment you perform in a windowless room will tell you whether the room is moving or standing still. Einstein simply extended this principle to encompass all of physics, including electromagnetism and optics. The second postulate was the revolutionary one. The speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. Read that again and let it sink in. The speed of light is the same for all observers. If I am standing still and you are flying toward me at half the speed of light, and a beam of light passes both of us, we will both measure that beam traveling at exactly the same speed, c. Not c minus your speed, not c plus my speed, just c, for both of us. This is deeply, profoundly counterintuitive. In everyday life, speeds add and subtract. If you're on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, someone standing on the platform sees the ball moving at 150 kilometers per hour. But light does not work that way. If you are on a train moving at half the speed of light and you shine a flashlight forward, someone on the platform will not see that light moving at 1.5 times the speed of light. They will see it moving at exactly c, the same speed as if you were standing still. This seems impossible. It seems like a contradiction. How can both observers measure the same speed for the same beam of light, even though they are moving relative to each other? The answer is that something else must give. And what gives is our intuitive understanding of space and time. Einstein realized that if the speed of light is truly constant for all observers, then space and time cannot be fixed, rigid, absolute quantities. They must be flexible, relative, dependent on the observer's state of motion. This is the heart of special relativity, and it has consequences that are nothing short of mind-bending. Let me walk you through the most important ones, starting with the one that demolishes our most basic assumptions about reality, the relativity of simultaneity. Consider this thought experiment. A train is moving along the tracks at tremendous speed. In the middle of the train, a light bulb flashes. The light travels in both directions, toward the front of the train and toward the back of the train. From the perspective of a passenger sitting in the middle of the train, the light reaches the front and the back of the train at exactly the same time. This makes sense because the passenger is at rest relative to the train, and the front and back are equidistant. The light travels the same distance in both directions and arrives simultaneously. Now, consider the perspective of an observer standing on the platform as the train passes. From their perspective, the back of the train is moving toward the point where the flash occurred, and the front of the train is moving away. Since the speed of light is the same in both directions, remember, it does not get a boost from the train's motion. The light heading toward the back of the train has a shorter distance to cover, because the back of the train is approaching it. The light heading toward the front has a longer distance, because the front of the train is receding from it. Therefore, from the platform observer's perspective, the light reaches the back of the train before it reaches the front. The two events, light reaching the front and light reaching the back, are not simultaneous for the platform observer. So, the passenger says the light arrived at both ends at the same time, and the platform observer says the light arrived at the back first. Who is right? Here is the staggering answer. Both are right. There is no absolute truth about which events are simultaneous. Simultaneity depends on your frame of reference. Two events that are simultaneous for one observer may not be simultaneous for another observer moving at a different speed. This is not an illusion. This is not a mistake or an artifact of measurement. This is the genuine, literal truth about the nature of time. Time is relative. Your time is not my time. My now is not the same as your now if we are moving relative to each other. Let that settle into your mind as you breathe slowly and deeply. The present moment, which seems so solid, so universal, so absolute, is actually personal. It depends on how you are moving through space. This leads directly to one of the most famous and well-tested predictions of special relativity: time dilation. Moving clocks run slow. If you are moving relative to me, I will observe your clock ticking more slowly than mine. And you, looking at my clock, will observe mine ticking more slowly than yours. This seems paradoxical, but it is resolved by the fact that we are in different reference frames and cannot directly compare clocks without bringing them together, which requires acceleration and breaks the symmetry. Let me explain time dilation with a beautiful thought experiment called the light clock. Imagine a clock that works by bouncing a photon of light back and forth between two mirrors, one at the top and one at the bottom, separated by a fixed distance. Every time the photon completes one round trip, the clock ticks once. Now, imagine this clock is on a spaceship moving at a high speed relative to you. From your perspective, the photon is not simply bouncing straight up and down. The clock is moving sideways, so the photon has to travel a diagonal path to go from the bottom mirror to the top mirror and back. This diagonal path is longer than the straight up and down path. But the photon must travel at the speed of light, which is constant. If the photon has to travel a longer path at the same speed, it takes more time to complete each round trip. Therefore, from your perspective, the moving clock ticks more slowly. Not because anything is wrong with the clock, not because the photon has slowed down, but because the geometry of spacetime itself requires that the moving clock runs slow. This is not just theoretical. Time dilation has been measured, confirmed, and verified in countless experiments. One of the most elegant demonstrations involves subatomic particles called muons. Muons are produced in the upper atmosphere when cosmic rays collide with air molecules. Muons are unstable and decay very quickly, with a half-life of about 2.2 microseconds. Given their speed and their short lifetime, muons should not be able to travel very far before decaying. They should decay long before reaching the ground, but they do reach the ground, in large numbers. The reason is time dilation. Muons are traveling at close to the speed of light, which means that from our perspective, their internal clocks are running slow. Their 2.2 microseconds of lifetime, as measured in their own rest frame, appears to be stretched out in our frame, giving them enough time to reach the ground before they decay. From the muon's perspective, it is the distance to the ground that has contracted, another consequence of relativity that we will discuss shortly. Either way, the muon reaches the ground. Both perspectives agree on the outcome but disagree on the explanation, and both are equally valid. Time dilation has also been directly measured using atomic clocks. In 1971, physicists Joseph Haefele and Richard Keating placed atomic clocks on commercial aircraft and flew them around the world in both directions. When they compared the airborne clocks to identical clocks that had remained on the ground, they found tiny but measurable differences, exactly as predicted by both special relativity, due to the aircraft's speed, and general relativity, due to the aircraft's altitude. The differences were on the order of nanoseconds, but they were real, and they matched Einstein's predictions with beautiful precision. Today, time dilation is not just a theoretical curiosity. It is a practical reality that affects the technologies you use every day. The Global Positioning System, GPS, relies on a network of satellites orbiting the Earth. These satellites carry extremely precise atomic clocks that are used to determine your position by measuring the time it takes signals to travel from the satellites to your device. But those satellite clocks are affected by both special relativistic time dilation, because the satellites are moving, and general relativistic time dilation, because the satellites are at a higher altitude in weaker gravity. If the GPS system did not correct for these relativistic effects, your position would drift by about 10 kilometers per day. Your GPS would be useless. Every time you use a map on your phone, every time a plane navigates by GPS, every time an emergency responder uses location services, relativity is at work. Einstein's abstract theory of 1905 is literally guiding you through traffic. Now, let me share with you one of the most famous thought experiments in all of physics: the twin paradox. Imagine you have a pair of twins. Let us call them Alice and Bob. Alice stays on Earth. Bob boards a spaceship and blasts off into space at 99% of the speed of light. He travels for 5 years, as measured by his onboard clock, to a distant star, then turns around and flies back at the same speed. When Bob returns and steps off his spaceship, he finds that while only 10 years have passed for him, 5 years out and 5 years back, decades have passed on Earth. Alice is now much older than Bob. This is not science fiction. This is not speculation. This is the direct, unambiguous prediction of special relativity, and it has been confirmed by every relevant experiment ever performed. The effect gets more dramatic as the speed increases. At 99.99% of the speed of light, a journey that takes 10 years for the traveler would see over 700 years pass on Earth. At 99.9999%, the disparity becomes even more extreme. The closer to the speed of light you travel, the more your personal time slows relative to the rest of the universe. You might wonder, is this really a paradox? After all, from Bob's perspective, it is Earth that is moving away at high speed, so should not Alice's clock be the one running slow? The resolution lies in the fact that the situation is not symmetric. Bob had to accelerate, turn around, and decelerate. He changed reference frames. Alice remained in a single inertial frame the entire time. This asymmetry is what breaks the paradox. The traveler who accelerates is the one who ages less. It is a strange and beautiful consequence of the geometry of spacetime. Time dilation is only half of the story. Special relativity also predicts that moving objects are physically shorter in the direction of their motion. This is called length contraction, and it is just as real and just as well tested as time dilation. The formula is elegant. The length you measure for a moving object equals its rest length multiplied by the square root of 1 minus v squared over c squared. At everyday speeds, this effect is negligibly small. A car driving at highway speed is shortened by an amount smaller than the width of a single atom. But at relativistic speeds, the effect becomes dramatic. At 87% of the speed of light, an object is compressed to half its rest length. At 99%, it is about 14% of its original length. A 100-meter spaceship moving at 99% of the speed of light would appear to be only about 14 meters long. At 99.99%, it would appear to be only about 1.4 meters long. And at the speed of light itself, its length would be 0. This contraction is not an optical illusion. It is not a distortion caused by the way light reaches your eyes. It is a genuine contraction of space itself in the moving object's frame. This is the same effect that Lorentz and Fitzgerald proposed to explain the Michelson-Morley experiment. But now it has a physical explanation. Objects contract because space and time are intertwined, because the geometry of space-time demands it. There is a wonderful thought experiment called the barn and pole paradox that illustrates just how strange length contraction can be. Imagine you have a pole that is 20 meters long and a barn that is only 10 meters long. The pole is clearly too long to fit inside the barn, but now imagine the pole is moving at a very high speed, say 87% of the speed of light. At that speed, length contraction reduces the pole's length by half to 10 meters. So from the barn's frame of reference, the pole fits neatly inside the barn. You could close the barn doors simultaneously at both ends, with the pole inside. But wait. From the pole's frame of reference, it is the barn that is moving, and the barn is contracted to only 5 meters. The pole is still 20 meters in its own frame. It clearly does not fit. So does the pole fit inside the barn or not? The answer is, it depends on your frame of reference. In the barn's frame, the pole fits, and both doors can be closed simultaneously. In the pole's frame, both doors do not close simultaneously. Due to the relativity of simultaneity, what appears as simultaneous door closings in the barn's frame appears as sequential events in the pole's frame. The front door closes and opens before the back door closes. At no point in any frame does anything impossible happen. The paradox is resolved by the realization that simultaneity is relative. Events that are simultaneous in one frame are not simultaneous in another. Now we come to what is perhaps the most famous equation in all of physics: E equals mc squared. Einstein derived this equation in the fourth paper of his miracle year, and its implications are staggering. The equation says that energy and mass are equivalent. They are two forms of the same thing, related by the speed of light squared. And because c squared is an enormously large number, about 9 times 10 to the 16 in SI units, a tiny amount of mass corresponds to a colossal amount of energy. How much energy? Let us put it in perspective. A single kilogram of matter, if completely converted to energy, would release about 90 quadrillion joules of energy. That is roughly the energy of a 20 megaton nuclear bomb. The Hiroshima bomb converted less than 1 gram of mass into energy. Less than 1 gram. The sun converts about 4 million tons of mass into energy every single second. And it has been doing so for 4.5 billion years, and it will continue for another 5 billion years. That is the power of E equals mc squared. But the equation also explains why nothing with mass can reach the speed of light. As an object moves faster, its kinetic energy increases. But in relativity, that energy has mass. So the faster you go, the more massive you become, and the harder it is to accelerate further. As you approach the speed of light, your effective mass increases without bound, approaching infinity. To accelerate an object with any mass at all to the speed of light would require an infinite amount of energy. And infinite energy is, by definition, more energy than exists in the entire observable universe. This is not a technical limitation. It is not that our rockets are not powerful enough. It is a fundamental, absolute limit built into the fabric of space-time. No amount of energy, no technology, no ingenuity, no civilization, no matter how advanced, can accelerate a massive object to the speed of light. The universe simply does not allow it. This is the reason the speed of light is a speed limit. It is not that light happens to be fast, and we have declared its speed to be the maximum. It is that the structure of space-time has a built-in maximum speed, and light travels at that speed because it has no mass. Anything without mass must travel at exactly c, not approximately, not closely, but exactly. And anything with mass must travel at less than c, always, forever, without exception. The speed of light is not the speed of light. It is the speed of the universe, the speed of space-time, the speed of causality. Light just happens to be one of the things that travels at this fundamental speed. Let me take a moment here to talk about something truly beautiful, something that I think captures the deepest answer to our central question. Why does light have a speed limit? The answer lies in the geometry of space-time. After Einstein published his special theory of relativity, one of his former professors, a mathematician named Hermann Minkowski, realized that Einstein's theory could be reinterpreted in a stunning geometric way. Minkowski showed that the 3 dimensions of space and the 1 dimension of time are not separate entities. They are woven together into a single 4-dimensional fabric called space-time. Every event in the universe, every moment, every location is a point in this 4-dimensional space-time. And the relationship between space and time is described by a mathematical structure called the space-time metric. Minkowski announced his insight in a famous 1908 lecture, declaring, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." Here is the remarkable thing. In Minkowski's space-time, everything, absolutely everything, moves through space-time at the speed of light. Always. Without exception. You, sitting still in your bed right now, are moving through space-time at the speed of light. A photon streaming across the universe is moving through space-time at the speed of light. A spaceship hurtling through space at 99% of c is moving through spacetime at the speed of light. How can this be? Because motion through spacetime has two components: motion through space and motion through time. These two components always add up, in the appropriate geometric sense, to the speed of light. If you are sitting still, not moving through space at all, then all of your motion through spacetime is directed through time. You are moving through time at the maximum rate. That is why time passes for you, because you are moving through the time dimension at the speed of light. Now, if you start moving through space, some of your motion through spacetime is diverted from time into space. You are now moving a little bit through space and a little bit less through time. Your time slows down. The faster you move through space, the more of your spacetime motion is diverted from time into space, and the slower your time passes. This continues until you reach the speed of light through space, at which point all of your motion through spacetime is directed through space and none through time. Time stops. This is why photons do not experience time. All of their motion through spacetime is through space. They have no motion left over for time. This is the deepest, most elegant answer to our question. Light does not have a speed limit. Everything has a speed through spacetime, and that speed is always c. What we call the speed of light is really the speed at which everything moves through the fabric of reality. Objects with mass can trade some of their motion through time for motion through space, but they can never reach c through space alone, because they always retain at least a tiny bit of motion through time. Only massless objects, like photons, can achieve full speed through space, and they do so at the cost of having zero motion through time. This is why the speed of light is what it is. It is the total speed of everything through spacetime. It is not a limit imposed on the universe from outside. It is the universe's own nature, expressed as a number. If you are still awake and your mind is gently humming with these ideas, I want to pause for just a moment. We have come incredibly far already. We have traveled from the ancient Greeks to Einstein, from particles to waves to quanta, from Galileo's hilltop lanterns to the Michelson-Morley interferometer, from the death of absolute time to the geometry of space-time. And we are just getting started. If you have not already subscribed to this channel, now would be a wonderful time. Hit that subscribe button and that bell icon so you do not miss the next deep dive. And if any of these ideas have made your jaw drop, even just a little, leave a comment down below. Tell me which part amazed you the most. Your comments are the fuel that keeps this channel going. Now let us take another great leap forward, from special relativity to general relativity. Special relativity, published in 1905, dealt with constant velocities. It described how space and time behave when objects move at constant speeds relative to each other. But it did not address acceleration or gravity. Einstein knew that his theory was incomplete. He spent the next 10 years from 1905 to 1915 working on a generalization of his theory that would include acceleration and gravity. It was the most intense intellectual struggle of his life, and the result was the general theory of relativity, which many physicists consider the most beautiful theory ever constructed. Einstein's starting point for general relativity was another thought experiment, one he later called the happiest thought of my life. Imagine you are in an elevator in outer space, far from any planet or star. The elevator is being accelerated upward at 9.8 meters per second squared, the same acceleration as gravity on Earth's surface. Inside the elevator, you would feel a force pushing you toward the floor. If you dropped a ball, it would fall to the floor. If you stood on a scale, it would show your normal weight. You could pour water, throw a ball, do jumping jacks, and everything would feel exactly like being on Earth. Now, here's the key insight. There is no experiment you could perform inside that elevator that would tell you whether you are being accelerated in space or standing still on the surface of Earth. The two situations are physically indistinguishable. Einstein elevated this observation to a fundamental principle, the equivalence principle. Gravity and acceleration are equivalent. They are the same thing. This might seem like a minor technical point, but its implications are revolutionary. If gravity and acceleration are equivalent, and if acceleration affects time, as special relativity shows, then gravity must also affect time. A clock in a strong gravitational field must tick slower than a clock in a weak gravitational field. And if gravity affects time, and time and space are intertwined in spacetime, then gravity must affect the geometry of spacetime itself. This is the central insight of general relativity. Gravity is not a force. It is the curvature of spacetime. Massive objects like stars and planets curve the fabric of spacetime around them, and other objects moving through that curved spacetime follow the straightest possible paths, which appear to us as orbits and falling trajectories. The physicist John Archibald Wheeler summarized it perfectly. Spacetime tells matter how to move, matter tells spacetime how to curve. The Earth does not orbit the Sun because the Sun pulls on it with some invisible force. The Earth orbits the Sun because the Sun's mass curves the spacetime around it, and the Earth is following the straightest possible path through that curved geometry. From the Earth's perspective, it is not being pulled. It is simply moving in a straight line through curved space. It is the straightest possible path, called a geodesic, but because the space itself is curved, that straight line happens to be a loop around the Sun. General relativity makes several remarkable predictions about how gravity affects light and time. First, gravitational time dilation. Time runs slower in stronger gravitational fields. A clock on the surface of the Earth ticks slightly slower than a clock on a satellite in orbit, because the Earth's gravity is stronger at the surface. This effect is real and measurable. The GPS satellites I mentioned earlier must correct for it. The clock at the bottom of a tall building ticks slightly slower than the clock at the top. This has been directly measured using incredibly precise atomic clocks. Near a black hole, where gravity is extraordinarily strong, time dilation becomes extreme. At the event horizon of a black hole, the boundary beyond which nothing can escape, time stops. An observer watching someone fall into a black hole would see them slow down and freeze at the event horizon, their image growing dimmer and redder, but never actually crossing it. From the falling person's perspective, they would cross the event horizon without noticing anything special, at least for a large enough black hole, but they could never send any signal back. The event horizon is the point of no return, and it exists because of the speed of light. The escape velocity at the event horizon equals c, and since nothing can exceed c, nothing can escape. General relativity also predicts gravitational lensing. Light follows curved paths through curved spacetime. When light from a distant galaxy passes near a massive object like a galaxy cluster, the spacetime curvature bends the light's path, causing the distant galaxy to appear distorted, magnified, or even split into multiple images. This effect has been observed countless times and is now used as a powerful tool in astronomy to map the distribution of dark matter in the universe. Einstein predicted gravitational lensing, and he also predicted another extraordinary phenomenon: gravitational waves. Just as a charged particle moving through space creates electromagnetic waves, a massive object accelerating through spacetime creates gravitational waves, ripples in the fabric of spacetime itself. These ripples spread out at the speed of light, stretching and compressing space as they pass. Einstein predicted them in 1916, but he doubted they would ever be detected, because the effect is incredibly small. He was wrong about that. In September 2015, almost exactly 100 years after Einstein's prediction, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time. The waves came from the merger of two black holes about 1.3 billion light-years away. The two black holes had spiraled toward each other, getting closer and closer, moving faster and faster, until they collided and merged into a single, larger black hole. The energy released in the final moments of the merger was staggering, briefly outshining the combined light of all the stars in the observable universe. And all of that energy was carried away as gravitational waves, ripples in spacetime, traveling at the speed of light. The detection of gravitational waves was not just a confirmation of Einstein's theory. It also confirmed something crucial about the speed of light. Gravitational waves travel at c. This is not a coincidence. The speed of light is not just the speed of electromagnetic waves, it is the speed of gravitational waves too. It is the speed at which any disturbance in spacetime propagates. It is the speed of causality. If the sun were to suddenly vanish, which it will not, but hypothetically, the gravitational effect of its disappearance would reach us at the same time as the visual effect, 8 minutes and 20 seconds later. Gravity and light travel at the same speed because they are both disturbances propagating through the same underlying medium, spacetime. Let me develop this point further because it is central to understanding why light has a speed limit. We have been calling it the speed of light, but that name is misleading. It suggests that this speed is somehow a property of light, something special about photons. But it is not. It is a property of spacetime. It is the speed at which any massless entity must travel. It is the speed at which any causal influence propagates. It is the maximum speed at which information can travel from one point in the universe to another. Physicists sometimes call it the speed of causality, which is a far more accurate name. Causality is the principle that causes must come before effects. If I throw a ball and it breaks a window, the throwing must happen before the breaking. If the speed of causality were infinite, then causes and effects could be arbitrarily close together in time, or even simultaneous, regardless of how far apart they are in space. But the speed of causality is finite, and it equals c. This means there is a minimum time between a cause at one location and its effect at another location, the time it takes light to travel between them. If two events are separated by a distance d, then at least a time d divided by c must pass between a cause at one event and its effect at the other. This creates a structure in spacetime called the light cone. Imagine you at a particular point in space and time. Your future light cone is the region of spacetime that you can possibly influence. It is defined by all the paths that light could travel outward from your location. Anything inside your future light cone can be affected by you. Anything outside your future light cone is beyond your reach. No signal, no influence, no causal connection. Similarly, your past light cone is the region of spacetime that could possibly have influenced you. It is defined by all the paths that light could have traveled inward to reach your location. Events inside your past light cone could have affected you. Events outside your past light cone have had no influence on you whatsoever. The light cone structure divides spacetime into causally connected and causally disconnected regions. Events outside each other's light cones are causally disconnected. They cannot influence each other in any way. They might as well be in separate universes. And the boundary of the light cone, the edge between what is reachable and what is not, is defined by the speed of light. The speed of light is the speed of causality, and it creates the fundamental structure of cause and effect in our universe. Now, let us go deeper and ask a question that few science videos dare to tackle. Why does c have the specific value it does? Why 299,792,458 meters per second and not some other number? This is a question that sits right at the boundary between physics and philosophy, and the honest answer is that we do not fully know. But we can say some illuminating things about it. First, the value of c depends on your choice of units. If you measure distance in feet and time in nanoseconds, cu is approximately 1 foot per nanosecond. In natural units, which are the units physicists use when they want to express things in the most fundamental way, c is simply defined to be 1. In these units, the speed of light is not 299,792,458 anything. It is just 1. This might seem like cheating, but it actually reveals something deep. The speed of light is the natural conversion factor between space and time. 1 second of time is equivalent to about 299,792 kilometers of space. They are the same thing, measured in different units, just as 1 mile equals 1.609 kilometers. The specific number 299,792,458 is not fundamental. It is an artifact of how we define meters and seconds. What is fundamental is that space and time are interchangeable, and the conversion factor between them is finite. But there is a number related to the speed of light that is dimensionless, meaning it does not depend on your choice of units, and therefore might be truly fundamental. It is called the fine structure constant, and it is approximately equal to 1 over 137, or, more precisely, approximately 0.007297. The fine structure constant, usually denoted by the Greek letter alpha, is a combination of the speed of light, Planck's constant, and the charge of the electron. Alpha equals E squared over 4 pi epsilon naught times h bar times c. This number determines the strength of the electromagnetic force, and it appears in all sorts of physical processes. It determines how strongly light interacts with matter, and it affects the structure of atoms, the properties of chemical bonds, and the nature of the visible spectrum. If the fine structure constant were significantly different from its actual value, the universe would be a very different place. If alpha were much larger, electromagnetic forces would be stronger, and atoms as we know them might not exist. Chemical bonds would behave differently, and complex molecules like DNA could not form. If alpha were much smaller, electromagnetic forces would be weaker, and atoms would be larger and more loosely bound. Stars might burn differently, and the chemistry of life might be impossible. The fact that alpha has the particular value it does, a value that appears to be finely tuned to allow for the existence of atoms, chemistry, and ultimately life, is one of the deepest mysteries in physics. Some physicists see this as evidence that the constants of nature are not random but have been selected by some process, whether by design or by a process of natural selection across a multiverse. Others see it as a question that may not have a meaningful answer, or that may point to a deeper theory that we have not yet discovered. The speed of light also has a relationship to the fundamental properties of empty space. Maxwell's equations give us c equals 1 over the square root of epsilon, naught times mu naught, where epsilon naught is the electric permittivity of free space, a measure of how easily an electric field can form in the vacuum, and mu naught is the magnetic permeability of free space, a measure of how easily a magnetic field can form. The speed of light is literally determined by how the vacuum responds to electric and magnetic fields. It is a property of empty space itself. This is a profound realization, The speed of light is not a property of light. It is not something light does. It is a property of the vacuum, of space-time itself, of the arena in which all of physics takes place. Light travels at c because the vacuum has the electromagnetic properties it has. Gravitational waves travel at c because space-time has the geometric properties it has. Any massless entity travels at c because that is the natural speed of causality in our space-time. The speed of light is the speed of the universe. This naturally leads to one of the most delightful thought experiments in all of physics. What would happen if the speed of light were different? Let us play this game for a while, because it beautifully illustrates how deeply the speed of light is woven into the fabric of reality. First, imagine the speed of light were much faster, say 1 trillion times faster. In such a universe, relativistic effects would be essentially undetectable. Even the fastest objects in the cosmos would be moving at a negligibly small fraction of c. The universe would behave almost exactly as Newton imagined: absolute space, absolute time, no time dilation, no length contraction, no meaningful connection between mass and energy. But E equals mc squared would still hold. And because c is so much larger, a given amount of mass would correspond to a vastly larger amount of energy. Nuclear reactions would be different. Stars would burn differently. The balance of forces in atoms and nuclei would shift. It is not clear that a universe with a much faster speed of light could support the structures we depend on for existence. Stable atoms, stable stars, stable planets, stable chemistry. Now imagine the speed of light were much slower, say only 100 kilometers per hour. This is the scenario that is truly fun to think about. In this slow light universe, you would encounter relativistic effects in everyday life. Driving your car at highway speed, you would experience noticeable time dilation. Your car would visibly contract in length. Colors would shift as you moved, with objects ahead of you appearing bluer and objects behind you appearing redder, due to the relativistic Doppler effect. Jogging through the park would cause noticeable distortions of time and space. GPS would be unnecessary because the speed of light would be so slow that you could measure distances directly by timing light signals with a wristwatch. But the universe would also be terrifying. Communication would be agonizingly slow. Telephone calls across a city would have noticeable delays. Seeing what is happening across the room would involve a perceptible lag. The entire pace of the universe would change. Stars would work differently, if they could work at all. The relationship between mass and energy would be fundamentally altered. A slow speed of light would mean E equals mc squared, produces much less energy for a given mass, since c is smaller. Nuclear reactions would be far less energetic. Stars might not be able to sustain fusion. The universe might be cold and dark. MIT researchers actually created a computer game called A Slower Speed of Light that lets you experience what it would be like to approach the speed of light in a universe where c is very slow. As you speed up, you see the visual distortions of relativity. Colors shift, objects ahead of you get compressed, objects behind you stretch out, and time slows down. It is a beautiful demonstration of how the speed of light shapes our perception of reality. And what if the speed of light were infinite? This is perhaps the most interesting scenario. If c were infinite, there would be no special relativity. Space and time would be completely separate, absolute and universal. Simultaneity would be absolute. Everyone would agree on what is happening now throughout the universe. There would be no time dilation, no length contraction, no light cones, no causal structure. Information could travel instantaneously from one end of the universe to the other. The universe would be a classical Newtonian place. But there would also be no E equals mc squared, because E equals m times infinity squared, which is infinite. Any mass would contain infinite energy. Matter and energy would not be equivalent in any meaningful sense. Nuclear reactions and the energy of the sun would have to be explained by entirely different physics. The universe as we know it would be utterly impossible. So the speed of light is not just some incidental property of the universe. It is a load-bearing pillar. Change it, and the entire structure of reality collapses and must be rebuilt from scratch, if it can be rebuilt at all. Now, let us turn to a question that has captured the imagination of physicists, science fiction writers, and dreamers everywhere. Can anything travel faster than the speed of light? The short answer is no. Nothing that carries information can exceed c. But the full answer is far more nuanced and fascinating, and there are several phenomena that seem to challenge the cosmic speed limit. Let us go through them one by one. The first and most famous apparent violation of the speed of light comes from quantum mechanics. Quantum entanglement. This is what Einstein famously called spooky action at a distance. Here's how it works. Certain quantum processes can create pairs of particles that are entangled, meaning their properties are correlated in a way that has no classical analog. For example, you can create a pair of photons such that their polarizations are correlated. You do not know the polarization of either photon individually, but you know that if you measure one and find it is vertically polarized, the other will be horizontally polarized, and vice versa. Now, here is the spooky part. You can separate these two entangled photons by any distance, even billions of light years, and when you measure one, you instantly know the state of the other. The correlation is instantaneous. It does not depend on the distance between the particles. If you measure one photon on Earth and find it is vertically polarized, the other photon, which might be at the other end of the galaxy, is instantly determined to be horizontally polarized. This seems to violate the speed of light. The information about the measurement result seems to travel from one photon to the other instantaneously, faster than light could travel between them. But here is the crucial subtlety. No usable information is transmitted. The result you get when you measure your photon is random. You cannot control it. You cannot send a message by choosing what result to get. The only way to verify the correlation is to compare your result with the result of the distant measurement, and that comparison requires classical communication, which is limited to the speed of light. This is formalized in a result called the no-communication theorem, which proves mathematically that quantum entanglement cannot be used to transmit information faster than light. The correlation is real. The instantaneous nature is real. But it cannot be exploited to send a signal, make a phone call, or transmit any usable information faster than c. The speed of light remains inviolate. The physicist John Bell made this even more profound in 1964 with what is now called Bell's theorem. Bell showed that the correlations predicted by quantum mechanics are stronger than any correlations that could be produced by local hidden variables, that is, by particles carrying predetermined instructions. Experiments testing Bell's theorem, beginning with Alain Aspect's experiments in the 1980s and continuing with increasingly rigorous tests in the 2010s, have conclusively confirmed that quantum mechanics is correct and that Bell inequalities are violated. The universe is genuinely non-local in some sense. Entangled particles are connected in a way that transcends space, but this non-locality does not allow faster-than-light communication. It is, in Einstein's words, spooky, but it is not a speed-of-light violation. The universe is stranger than Einstein hoped, but it still respects the cosmic speed limit when it comes to information transfer. The second phenomenon that seems to exceed the speed of light is the expansion of the universe itself. Galaxies far enough away from us are receding at speeds that exceed the speed of light. This is a real, measurable fact. Galaxies at the edge of the observable universe are receding from us at roughly 3 times the speed of light. How is this possible without violating relativity? The answer is that these galaxies are not moving through space faster than light. It is space itself that is expanding, carrying the galaxies along with it. Imagine 2 ants on a rubber band. The ants are walking toward each other at a fixed speed, but someone is stretching the rubber band. If the rubber band is being stretched fast enough, the ants will get farther apart even though they are both walking toward each other. The ants' speed through the rubber is limited, but the stretching of the rubber itself has no speed limit. Similarly, the expansion of space can carry galaxies apart faster than light, but no galaxy is moving through its local space faster than light. This distinction is crucial. Relativity says that nothing can move through space faster than light, but it places no limit on the expansion of space itself. This has profound consequences. Galaxies that are currently receding from us faster than light are beyond our cosmic horizon. Light from those galaxies, traveling toward us at sea through space, is nonetheless being carried away from us by the expansion of space faster than it can approach. We will never see the light from those galaxies. They are forever beyond our reach. The observable universe has a boundary, and that boundary is defined by the expansion rate of space and the speed of light. The third phenomenon is more of a mathematical curiosity, but worth mentioning. The phase velocity of a wave can exceed the speed of light. In certain media, the individual wave crests of light move faster than c. This is related to how the wave interacts with the medium and involves the relationship between the wave's frequency and the medium's refractive index. But the phase velocity is not the speed at which information or energy travels. That is the group velocity, which never exceeds c in any physical medium, when properly defined for signal transmission. A simple analogy is a laser pointer sweeping across the surface of the moon. If you quickly flick your wrist, the bright dot can traverse the moon's surface faster than light, but no information is traveling from one part of the moon to the other. The photons hitting the moon at each moment are different photons, arriving independently from the laser on Earth. The dot is not a physical object moving across the surface. It is a series of independent events that, taken together, create the illusion of motion. Similarly, a shadow can move faster than light. If you place your hand near a bright light and quickly move it, the shadow on a distant wall can sweep across the wall faster than light. But again, no information is being transmitted. These are not true violations of the speed of light because they do not involve the transmission of information, energy, or causal influence. There is also Cherenkov radiation, which I want to tell you about because it is beautiful and fascinating. In a vacuum, nothing can exceed the speed of light, but in a medium like water, light slows down. In water, light travels at about 75% of its vacuum speed. This means that a fast-moving particle, such as an electron from a nuclear reaction, can travel through water faster than light travels through water. When this happens, the particle creates a shock wave of light, analogous to a sonic boom created by an aircraft exceeding the speed of sound. This shock wave of light is called Cherenkov radiation, and it produces a hauntingly beautiful blue glow. If you have ever seen photographs of a nuclear reactor core submerged in water, you may have noticed a ghostly blue light surrounding the core. That blue glow is Cherenkov radiation, created by particles from the nuclear reactions moving faster than light in water. It is one of the most beautiful phenomena in physics, but it does not violate the cosmic speed limit because the particles are not exceeding c, the speed of light in vacuum. They are only exceeding the speed of light in water, which is a slower local speed. Now, what about hypothetical particles called tachyons? Tachyons are theoretical particles that are born traveling faster than light and can never slow down to the speed of light or below. Just as normal particles, called tardions or bradyons, are always slower than light and need infinite energy to reach c, tachyons would always be faster than light and would need infinite energy to slow down to c. The speed of light would be a barrier from both sides. Tachyons were first seriously discussed in the 1960s by physicists Gerald Feinberg, George Sudarshan, and others. In the mathematical framework of special relativity, tachyons are consistent in the sense that they do not lead to immediate mathematical contradictions. However, they have a deeply problematic property. They travel backward in time. Because tachyons exceed c, there exist reference frames in which a tachyon arrives at its destination before it leaves its source. This leads to causal paradoxes, like the ability to send a message to your own past, which in turn leads to logical contradictions like the grandfather paradox. For this reason, and because no tachyon has ever been detected in any experiment, most physicists believe tachyons do not exist. If they did, they would fundamentally undermine the principle of causality, which is one of the bedrock principles of physics. But what if we could travel faster than light without actually moving through space faster than light? What if, instead of moving through space, we could move space itself? This is the idea behind the Alcubierre warp drive, proposed by Mexican physicist Miguel Alcubierre in 1994. Alcubierre showed that Einstein's equations of general relativity technically allow for a configuration of spacetime in which a bubble of flat spacetime moves through the larger spacetime at an arbitrarily high speed. Inside the bubble, everything is perfectly normal. You are not moving at all relative to your local spacetime. But the bubble itself is being transported faster than light by the contraction of space in front of it and the expansion of space behind it. It is like a surfer riding a wave. The surfer is not moving through the water, but the wave carries them forward. The Alcubierre warp drive does not violate special relativity because the spacecraft inside the bubble is not moving through space faster than light. It is the space around the bubble that is being manipulated. In a sense, the universe already does this with the expansion of space. Distant galaxies are carried away from us faster than light by the expanding universe. Alcubierre's proposal just does it in a controlled, directed way. However, there are enormous practical problems. The warp drive requires exotic matter, matter with negative energy density, to create the spacetime distortion. We do not know if such matter exists. The original calculations showed that the energy requirements would be absurdly large, more than the mass energy of the entire observable universe. Subsequent work by various physicists, including Harold White at NASA, has reduced the energy requirement somewhat by modifying the shape of the warp bubble, but the requirements remain far beyond anything we could currently achieve. There are also deep theoretical concerns about Hawking radiation inside the bubble, about the stability of the configuration, and about the fundamental question of whether causality is preserved. If you can travel faster than light, even indirectly, the same causal paradoxes that plague tachyons may apply. The warp drive remains a fascinating theoretical possibility, but it is currently in the realm of speculation rather than engineering. Another potential shortcut through spacetime is the wormhole, also known as an Einstein-Rosen bridge. Wormholes arise naturally from the mathematics of general relativity. Imagine spacetime as a sheet of paper. Two distant points on the paper are far apart if you travel along the surface. But if you fold the paper so the 2 points are close together, you could poke a hole through both layers and create a shortcut. A wormhole would be such a shortcut through higher dimensional spacetime, connecting two distant points in the universe, or potentially even two different universes. The concept was first discussed by Einstein and his colleague Nathan Rosen in 1935, and later developed by John Wheeler and Kip Thorne, among others. In 1988, Thorne and his colleagues showed that a traversable wormhole, one that a person could actually travel through, would be theoretically possible if it were stabilized with exotic matter, the same kind of negative energy matter required for the Alcubierre warp drive. Without exotic matter, a wormhole would collapse so quickly that nothing, not even light, could pass through it. Even with exotic matter, there are serious concerns about stability, quantum effects, and the potential for causality violations. If a wormhole connects two points in space, and one end is moved at high speed or placed in a strong gravitational field so that time passes differently for the two ends, the wormhole could potentially become a time machine. This leads to the same causal paradoxes that physicists find deeply troubling. Stephen Hawking proposed a chronology protection conjecture, suggesting that the laws of physics conspire to prevent time travel, perhaps through quantum effects that would destroy any wormhole on the verge of becoming a time machine. Whether this conjecture is correct remains an open question. There is one more faster-than-light concept I want to mention, because it connects beautifully to both quantum mechanics and general relativity. It is the ER equals EPR conjecture, proposed by Leonard Susskind and Juan Maldacena in 2013. ER refers to Einstein-Rosen bridges, wormholes, and EPR refers to the Einstein-Podolsky-Rosen paradox, quantum entanglement. The conjecture suggests that every pair of entangled particles is connected by a wormhole. Not a traversable wormhole that you could travel through, but a tiny, quantum-scale wormhole that connects the two particles through the fabric of spacetime. If this is true, it would mean that quantum entanglement and spacetime geometry are fundamentally the same phenomenon. It would mean that the spooky, non-local connections of quantum mechanics are actually local connections through a hidden dimension of space. This is one of the most exciting ideas in modern theoretical physics, and it has deep implications for our understanding of both quantum mechanics and gravity. It suggests that spacetime itself may be woven from quantum entanglement, that the very fabric of the universe is a network of entangled quantum states, and the speed of light, the cosmic speed limit, might emerge from the structure of this network. Let us now venture into the quantum world to explore how light behaves at the most fundamental level. We have already discussed the wave-particle duality of light, but there is so much more to the quantum story. In the modern framework of physics, light is described by a theory called quantum electrodynamics, or QED. QED is the quantum theory of the electromagnetic force. It was developed in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, who shared the Nobel Prize for their work. QED describes how light, photons, interacts with electrically charged particles, like electrons and quarks. It does this using the language of quantum fields. The electromagnetic field is a quantum field that permeates all of space, and photons are excitations of this field, like ripples on a pond. When two electrons repel each other, QED describes this interaction as the exchange of virtual photons between them. Virtual photons are not real photons. They do not propagate through space and reach a detector. They are mathematical objects that represent the influence of the electromagnetic field. But they are essential to the theory's predictions. QED is the most precisely tested theory in the history of science. Its predictions match experimental measurements to an extraordinary degree. The most famous example is the anomalous magnetic moment of the electron. QED predicts this quantity to over 10 decimal places, and the prediction matches the experimental value perfectly at every decimal place. To put this in perspective, If you predicted the distance from New York to Los Angeles to the same precision, you would be accurate to within the width of a human hair. No other theory in any field of science has ever achieved this level of agreement between prediction and measurement. QED's success is a testament to the power of quantum field theory and to the fundamental correctness of the framework in which the speed of light plays a central role. But QED reveals something strange and wonderful about how light actually travels. In the classical picture, light travels in straight lines at the speed of c. In the quantum picture, things are far more subtle. Richard Feynman developed a beautiful way of thinking about quantum mechanics called the path integral formulation, also known as the sum over histories approach. In this approach, a photon traveling from point A to point B does not follow a single path. It follows all possible paths simultaneously. Every conceivable path, including paths that zigzag, loop around, go backward in time, detour through distant galaxies, and generally violate every intuition about how a well-behaved particle should travel. Each of these paths has a complex number associated with it, called an amplitude. To calculate the probability of the photon going from A to B, you add up, integrate over, the amplitudes for all possible paths. This is where the magic happens. For most of the crazy, zigzagging paths, the amplitudes point in wildly different directions and cancel each other out. But for paths that are close to the classical straight-line path at the speed of light, the amplitudes all point in nearly the same direction and reinforce each other. The result is that the photon appears to travel in a straight line at the speed of light, but this behavior emerges from a quantum sum over an infinity of paths, most of which are nothing like a straight line. The speed of light in Feynman's picture is not a speed that light has. It is the speed that emerges when you sum over all possible histories, and the interference pattern favors paths at c. Light does not know to travel at c. The speed c emerges from the mathematics of quantum fields, from the structure of spacetime, from the fundamental properties of the vacuum. This connects to another deep question. What is the vacuum? In classical physics, the vacuum is empty space, a void with nothing in it. In quantum field theory, the vacuum is anything but empty. It is a seething, roiling sea of quantum fluctuations. Virtual particles are constantly being created and annihilated, popping into existence for the briefest of moments and then disappearing again. This is not metaphorical. It is real and measurable. The most famous experimental evidence for vacuum fluctuations is the Casimir effect. If you place two uncharged metallic plates very close together in a vacuum, they experience a tiny attractive force, pulling them together. This force arises because the quantum fluctuations between the plates are restricted. Only certain wavelengths fit between them, while the fluctuations outside are unrestricted. The difference in fluctuation energy creates a measurable force. The Casimir effect has been measured with high precision and matches the theoretical prediction beautifully. Some physicists have speculated that the speed of light might be determined by the properties of the quantum vacuum. In this view, the vacuum is not merely empty space but a medium with specific electromagnetic properties, epsilon naught and mu naught. And these properties set the speed of light just as the density and elasticity of a material set the speed of sound in that material. If this view is correct, then the speed of light is not a fundamental constant in the deepest sense. It is an emergent property, arising from the quantum structure of the vacuum. Changing the properties of the vacuum would change the speed of light. This is an active area of research, and it connects to some of the most profound, open questions in physics. There is another quantum phenomenon I want to tell you about that relates to our story in a fascinating way. It is called the delayed choice quantum eraser, and it probes the relationship between light, measurement, time and causality. The experiment is a variation of the double-slit experiment. In the standard double-slit experiment, light passes through two slits and creates an interference pattern on a screen. If you try to detect which slit each photon passes through, the interference pattern disappears. The act of measurement, of gaining which path information, destroys the wave-like behavior and produces a particle-like pattern. The delayed choice experiment adds a twist. After the photon has already passed through the slits and been detected on the screen, you choose whether or not to obtain which path information. And the mind-blowing result is that your choice, made after the photon has already been detected, seems to affect whether the photon behaved as a wave or a particle when it passed through the slits. If you choose to erase the which path information, the interference pattern appears in the data. If you choose to keep it, the pattern disappears. It is as if the photon went back in time and adjusted its behavior based on your future decision. This seems to suggest that the future can influence the past, which would be a flagrant violation of causality and the speed of light. But careful analysis shows that no information actually travels backward in time. The interference pattern is only visible when you correlate the data from the screen with the data from the eraser, and that correlation requires classical communication, which is limited to the speed of light. There is no way to see the interference pattern on the screen alone without the correlated data. So, causality is preserved, but the experiment reveals just how deeply strange quantum mechanics really is, and how the speed of light stands as the ultimate guarantor of causal order in a universe where the rules of quantum mechanics can seem to mock our intuitions about time and causality. Now, let us zoom out and consider the cosmic implications of the speed of light. We have talked about what the speed of light is, why it exists, and what would happen if it were different. But I want you to appreciate what it means for us, for humanity, for our place in the universe. The speed of light creates the observable universe. Light has had about 13.8 billion years to travel since the Big Bang. In that time, it has traveled about 13.8 billion light-years. But the universe has been expanding during that time, so the regions of space from which that light originally came are now about 46.5 billion light-years away in every direction. This gives us an observable universe that is about 93 billion light-years across. Beyond this boundary, the rest of the universe, which might be infinitely large, is forever hidden from us. Light from those regions has not had enough time to reach us, and because the expansion of space is accelerating, driven by dark energy, much of that light will never reach us, even if we wait forever. The speed of light creates a cosmic horizon, a boundary beyond which we cannot see and will never see. Within the observable universe, the speed of light creates something beautiful and poignant. Because light takes time to travel, when we look at distant objects, we see them as they were in the past. The moon is 1.3 light seconds away, so we see it as it was 1.3 seconds ago. The sun is 8.3 light minutes away. Mars, at its closest approach, is about 3 light minutes away. Jupiter is about 35 to 52 light minutes away, depending on its position. The nearest star, Proxima Centauri, is 4.24 light-years away. The center of our galaxy is about 26,000 light-years away. The Andromeda Galaxy, the nearest large galaxy, is 2.5 million light-years away. And the most distant galaxies we can observe are over 13 billion light-years away. Every time you look at anything, you are looking back in time. Even reading these words on your screen, you are seeing the screen as it was a few nanoseconds ago, the time it took the light to travel from the screen to your eyes. The further away something is, the further back in time you are seeing. Telescopes are the most powerful time machines ever built. The James Webb Space Telescope can see galaxies that formed just a few 100 million years after the Big Bang. It is literally looking back in time over 13 billion years. The cosmic microwave background, the faint radiation left over from the Big Bang, is the oldest light we can detect. It is the fossil light of the universe's birth, stretched by billions of years of cosmic expansion into microwaves. When we observe the CMB, we are seeing the universe as it was about 380,000 years after the Big Bang, when atoms first formed and the universe became transparent to light. The speed of light also creates a profound cosmic loneliness. The distances between stars, galaxies, and other cosmic structures are so vast that even at the speed of light, travel times are measured in years, centuries, millennia, and even millions or billions of years. The nearest star system is over 4 light-years away. At the speed of our fastest spacecraft, about 70,000 kilometers per hour, it would take roughly 80,000 years to reach it. Even at 1% of the speed of light, which is far beyond our current capabilities, the trip would take over 400 years. And that is just the nearest star. Most stars in our galaxy are tens of thousands of light-years away. Other galaxies are millions or billions of light-years away. The speed of light is incredibly fast by everyday standards, but on cosmic scales it is agonizingly slow. We can see these distant galaxies, these ancient wonders, but we can never visit them. Not in our lifetimes, not in the lifetime of our species, perhaps not ever. The speed of light gives us a view of a vast, magnificent universe while simultaneously placing most of it permanently out of reach. It is like being able to see a beautiful landscape through a window, but never being able to walk outside. This has implications for one of the most famous questions in all of science, the Fermi paradox. If the universe is so vast and so old, and if the conditions for life are not particularly rare, then where is everyone? Where are the alien civilizations? One possible answer is that the speed of light creates an effective quarantine. Even if intelligent civilizations are common in the universe, the distances between them, combined with the speed of light limitation, might make it practically impossible for them to find each other, visit each other, or even communicate in any meaningful way. The universe might be teeming with intelligent life, each civilization gazing up at the same sky, asking the same question, and the speed of light keeps them all isolated, alone, forever wondering. But there is another side to this cosmic loneliness, and it is beautiful. The speed of light means that the universe preserves its own history. Because light takes time to travel, the universe is an archive of itself. The light from every event, every explosion, every birth and death of a star radiates outward in an expanding sphere, traveling forever at sea. The light from the first stars that formed after the Big Bang is still out there, still traveling, still carrying information about those primordial furnaces. The light from the supernova that created the heavy elements in your body is still out there. In a very real sense, nothing is ever truly lost in the universe. Every event leaves its mark in light, and that light travels outward forever, a cosmic record etched into the fabric of spacetime. The speed of light also plays a crucial role in the ultimate fate of the universe. We now know that the expansion of the universe is accelerating, driven by a mysterious force called dark energy. As the expansion accelerates, more and more galaxies will cross our cosmic horizon and become unreachable and invisible. In the far future, billions and trillions of years from now, observers in our galaxy will look up at the sky and see nothing. All the other galaxies will have receded beyond the horizon. The cosmic microwave background will have stretched to undetectable wavelengths. The evidence for the Big Bang itself will have faded away. Future astronomers, if there are any, will look out at a universe that appears to contain only their own galaxy, floating in an infinite empty void. They will have no way to discover the true nature of the cosmos, because the speed of light combined with the accelerating expansion will have erased the evidence. All the light we now treasure, all the data from distant galaxies and ancient radiation will be gone, carried beyond the cosmic horizon by the inexorable expansion of space. This is a haunting thought, but it also underscores the preciousness of our moment in cosmic history. We live at a time when we can still see the evidence, when the universe is still revealing its secrets to us through the light that has had time to reach us. In a sense, we are among the last generations who will have access to the full story of the cosmos. The speed of light has given us a window, and that window is slowly, inexorably closing. Now, I want to explore a question that sits at the frontier of physics. Has the speed of light always been the same? We tend to think of the speed of light as an eternal, unchanging constant, the same today as it was at the moment of the Big Bang. But is this really true? Some physicists have proposed that the speed of light might have been different in the early universe. The most notable proponent of this idea is the Portuguese-born physicist João Magalhães, who, along with Andreas Albrecht, proposed a variable speed of light, VSL cosmology, in the late 1990s. Their motivation was the horizon problem, one of the big puzzles in cosmology. The cosmic microwave background is remarkably uniform in temperature, to about 1 part in 100,000. But regions on opposite sides of the sky are so far apart that light has not had time, since the Big Bang, to travel between them. They have never been in causal contact. So, how do they have the same temperature? In the standard cosmological model, this problem is solved by inflation, a brief period of exponentially rapid expansion in the very early universe that stretched a tiny, causally connected region to cosmic scales. But Magalhães and Albrecht proposed an alternative. What if the speed of light was much faster in the very early universe? If c were much larger in the first fraction of a second after the Big Bang, then light could have traversed the entire observable universe, bringing it to thermal equilibrium, before the speed of light settled down to its current value. This would solve the horizon problem without inflation. VSL theory is controversial and has not gained mainstream acceptance, partly because it is difficult to formulate precisely, since so much of physics is built on the constancy of c, and partly because inflation has been very successful at explaining the observed features of the CMB. But it has not been definitively ruled out, and it remains an active area of research. Related to VSL theories is the question of whether the fine structure constant alpha has changed over time. In the late 1990s and early 2000s, astronomer John Webb and his colleagues analyzed light from distant quasars that had passed through intervening gas clouds. The absorption lines in this light are sensitive to the value of alpha. Webb's team found evidence that alpha might have been slightly different in the past, smaller by about 1 part in 100,000. If true, this would be a momentous discovery, suggesting that the constants of nature are not truly constant but evolve over time. However, other groups have not been able to replicate the result, and the evidence remains controversial. The question of whether the speed of light or other fundamental constants change over time is one of the most important open questions in physics. There is also the tantalizing possibility that the speed of light might be different in different regions of space, or in different dimensions. In string theory, the leading candidate for a theory of quantum gravity, the universe has more than 3 spatial dimensions. The extra dimensions are thought to be curled up on incredibly small scales, too small to observe directly. It is possible that the speed of light depends on the geometry of these extra dimensions, and if that geometry varies from place to place or changes over time, c could vary as well. In brain world scenarios, where our observable universe is a three-dimensional membrane, or brane, floating in a higher dimensional space, the speed of light on the brane might be different from the speed of light in the bulk, the higher dimensional space. These are speculative ideas, but they illustrate how our understanding of the speed of light might change as we develop a deeper theory of quantum gravity. Let me now take you to a realm that lies at the intersection of physics and philosophy, a place where the speed of light reveals something about the deepest nature of reality. One of the most profound questions raised by the speed of light is, what kind of universe has a maximum speed? Think about it. In our everyday experience, there is no maximum speed. You can always go a little faster by pushing a little harder. But the universe says no, there is a limit. There is a number beyond which nothing can go. This is deeply strange, and it has led some thinkers to draw provocative analogies. In a computer simulation, there is a maximum speed at which information can propagate through the system. It is determined by the clock speed of the processor and the structure of the simulation. Could the speed of light be the clock speed of the universe? Could the fact that there is a maximum speed suggest that reality itself is some kind of computation, some kind of information processing system? This idea, known as the computational universe hypothesis or digital physics, has been explored by physicists like Konrad Zuse, Edward Fredkin, and Seth Lloyd. It is highly speculative, but it is intriguing that the speed of light behaves in some ways like a computational constraint. The Planck length, about 1.6 times 10 to the negative 35 meters, and the Planck time, about 5.4 times 10 to the negative 44 seconds, might represent the minimum units of space and time, the pixels and clock ticks of reality. The speed of light is simply the Planck length divided by the Planck time. If spacetime is quantized at the Planck scale, the speed of light would naturally emerge as the ratio of these minimum units, just as the maximum speed of propagation in a cellular automaton is 1 cell per time step. The speed of light also forces us to confront the nature of time in a very direct way. Before Einstein, time was thought to be absolute. Everyone experienced the same time, ticking away at the same rate, everywhere in the universe. The present moment was a universal concept. Everyone agreed on what was happening now. But special relativity destroyed this picture. Because the speed of light is finite and constant, and because simultaneity is relative, there is no universal now. Different observers, moving at different speeds, will disagree about which events are simultaneous. This leads to a philosophical position known as the block universe, or eternalism. In the block universe, all of time, past, present, and future exists equally. The past has not disappeared. The future has not yet to come into being. They are all there, laid out in the four-dimensional block of spacetime, like frames of a movie that all exist simultaneously on the film strip. What we experience as the flow of time is an illusion, or at least a subjective experience that does not correspond to any objective feature of spacetime. The block universe is a natural consequence of special relativity. If there is no absolute now, if different observers disagree about which events are simultaneous, then there is no objective division of spacetime into past, present, and future. All of spacetime must be equally real. Some physicists and philosophers embrace this view. Others resist it, arguing that our experience of time's passage is too vivid and too fundamental to be dismissed as an illusion. The debate continues, but it is remarkable that such a deep philosophical question about the nature of time and reality arises directly from the physics of the speed of light.